All right, hi. So as mentioned when on the Facebook app, when we talk about performance, there are really two problems that we're interested in, which is scroll performance and startup time. When talking about any performance problem, usually the first one that you want to tackle is finding the right metric. And unfortunately, in the scroll performance world, there's not necessarily an easy answer. So we spend a lot of time trying to find the right metric. Now, suppose when you use an iOS device, you're going to try to render about 60 frames per second, which means you have 16.6 milliseconds to render one frame. Now, in practice, that gives you maybe 8 milliseconds, if you're lucky, on the main thread. And usually, the bad experiences that a user will encounter is whenever your frame takes too long to render, which is if you miss the window. So 33 milliseconds if you miss one frame, or more if you go all the way to 100. So we figure out, well, 100 milliseconds is pretty bad. And when I scroll on my phone, I can see, oh, 100, that's like, it looks really bad. So we're going to try to reduce that number down. So we're going to drive down the number of frames that are rendered over 100 milliseconds. Now, immediately, there are two problems that shows up with that. The first problem is that the more people using your app, the more bad frames you're going to have. And it doesn't mean that your scroll view is bad. It just means more people are using your app. The second problem we had with this metric is that, relatively speaking, the frames that are rendered over 100 milliseconds are pretty rare, which means they might happen like every 2 minutes or every 3 minutes with an iPhone 6. And that's pretty bad because they could happen for like any number of reasons, that are completely outside of your control. Like a notification happens, the Bluetooth connection started waking up. The network connectivity switched from one hand to the other, the CPU was using it, and so on. And so for these reasons, we moved away from these events pretty quickly. So we moved on to some events that are like way more common, which is dropping only one frame, which your scroll view is definitely doing. And that solved quite a few problems. Now, it didn't solve all the problems, and especially what it didn't do is suppose that your frames that were taking like 100 milliseconds now take 200 milliseconds. It gets a lot worse, but this is not reflecting by your metric. So we switched that out, and we went for another metric, which is time spent. Now, time spent is a lot more interesting because it accounts for the bad frames getting worse. And so we were aiming for the percentage of time spent at 30 frames per second. And that was pretty good. The only problem of that metric is that it's a percentage, and so it's going to vary between like 98% to 99% on an iOS device. And that doesn't communicate really well within a big organization. Typically, if you try to go to a team and says, hey, like because of your change, the scroll performance went from like 99% to 98.5, it doesn't really resonate, but it's a huge change. And from the user perspective, like the scroll view is a lot worse. So we moved away from that, and we decided to settle on the number of seconds between 4 frame drops. And the advantage of that is like it's about the same metric if you do the math, but the big advantage is like it's easier to communicate. And typically, for instance, if you use the Facebook iPhone app, this is going to happen about every 12 seconds. If you have an iPad Air, it's going to be every 20 seconds. All right, so now we have our metric, and we don't want it to regress. How do you find a regression? And I'm going to start with the standard way. So the standard way is to use starting with Time Profiler. And Time Profiler is an Apple instrument that looks a lot like this, if you've ever used it. And what it does is that it's going to sample the CPU typically every millisecond and give you the stack traces on every thread. Lovely. The problem is like you don't know exactly which CPU time spent caused your frame drop. It could be anywhere in that big window. So you can use another trick on top of that, which is called signpost. And what it does is that it allows you to put little flags in the time profiler and to exactly identify the precise moment where you drop the frame. Well, that's great, but you can drop a lot of frames. Typically, like if you scroll for 10 minutes, you're going to drop thousands of frames, well, hundreds. And so you're going to have a lot of flags. So you look at all the flags, and you try to aggregate all all the CPU time spent, and you try to find then where your CPU is going. This gets to the next level, which is after that, you probably want to automate that to make a test that's repeatable, and you're going to try to use UI automation. And then finally, after that, you want a lab of devices so that you can run your devices. Now, that's all good and well, and it works pretty well, and we have that, but it's a lot of work, right? You have to set up all that infrastructure. And so we came up with an alternative way that I'm going to describe today. And we call it the CPU profiler. Essentially, the idea is that you ship with your code some instrumentation, and you let your app testers getting the data for you. So you have a population of app testers. Typically at Facebook, this is ranging in the thousands. And you add the performance thread that I'm going to talk about in a minute that's going to essentially monitor the main thread. And whenever you drop a frame, you collect the data about the frame that you just dropped, and you report that back to the server. Now, having that data on the server side is really, really interesting. Unlike a .trace file, you can parse that in any way you want. You can put that into any analytics framework that you prefer, and you could cut that down by types of CPU, types of device, OS version, iOS 8 versus iOS 9, and all these interesting drop-downs that you probably need. Now, how does it work under the hood? So it starts essentially, you have your frame windows that are running every 16 milliseconds. And you have the main thread who is doing work in order to render these frames. That can take any amount of time. And you have the performance thread that's just firing signals constantly. And we're talking like POSIX signal, like really just low-level stuff. And when the main thread receives the signal, it captures the backtrace, stored in memory. And if we ever drop the frame, which is we're taking more than 16.6 milliseconds, we look back at all the stack traces that we had, and then we send that back to the server. Compress it locally, aggregate it, send it back to the server. Now, the amazing thing about this is that it actually works, which is quite unexpected. It's pretty mind-blowing that the signal capturing is not too slow enough to damage your perf. We've run that test for quite a while at Facebook. This technology has been around for about 6 months. And essentially, there's no way to tell the difference whether or not like you're inside you're measuring via signal or you're not measuring. So the impact is pretty small. To give you an idea, capturing a backtrace will typically take 1 microsecond on an iPhone 4S. Which is the thousandth of a millisecond, which means you have quite a bit of time. So what kind of regression did we found? So we found a lot of complex code behaving in ways that we didn't expect. That was like the most common finding, which is essentially a path in the usage of our app that we didn't quite expect. So you would open the notification tab because you look at your notification on your Facebook app, then you go to the main feed, and then suddenly the notification tab tried to do something. And that is going to take some CPU cycles, and then the feed now, while you're scrolling, is dropping frames. And that was really, really common, and this is the kind of problems that we found. And it would be really hard to try to write a unit test or like an end-to-end test that would reproduce all these scenarios, because there's so many of them. Other problems that we found were essentially problems that are related to the battery life. Which is typically when the battery life of your device is going to get low, your device is going to behave quite differently, and we find a lot of code paths that would damage even more the battery life than damaging even more the scroll performance. And finally, one of the most complex and easier to find problems that we found was around videos. So if you have videos in a scroll view, you have to be really careful about how you handle it on iOS. And one thing you should never do is try to access the video player item properties on the main thread. And eventually, we found out that there was a bug where, depending on the very rare encoding on our platform, that would essentially cause us to access the bitrate and then drop a lot of frames. Now, finding this bug, trying to like write a test would require, like, for instance, trying all the encodings on our local device, which would take a lot of work. But using the CPU profiler, we can just leverage our population of app testers. And if they ever encounter this video, then again, the whole process works. We get the stack trace on the device. And it was actually really, really easy to fix once we know where the regression was, thanks to the CPO profiler. So all in all, the number one thing was finding the right metric, which right now for Facebook has been the number of seconds between drop events, whether it's 4 or 5, whatever the focus you want to be on. Building the right tools. We have sort of the standard way and the more advanced way using the CPO profiler. And as a result, we have a faster app and people are happier. And so now Greg is going to talk about another very interesting problem in performance, which is startup. Thank you.
Thanks, Clement. So just as scroll perf is central to people while they're using the application, to know that the app feels good and is performant, the other place where performance tends to fall down is when the user starts the application and then sits at the screen for a long period of time waiting to get responses back. And that will lead to people going, man, this app is really slow if you're not moving really quickly. And so let's start off and look at the progress that we made in roughly since the beginning of the year. So that's a really stark difference, and this is actually captured on a high-end device on a high-end network. And if you were looking at this on a low-end device on a weak network, the view would be even more clear as to how much it changed. And so how did we do that? So the first thing we did, which is the sort of thing you want to do anytime you're working on a performance problem, is you want to understand where the time is actually being spent inside of your applications in production. So we broke the startup into 3 pieces. First, we have the time from when the user starts the application until we actually send out our feed network request asking for stories. Then there's some period of time between that and when the server actually sends a feed network response back to us. And then we have the third leg, which is on the client from once we get that network response to when we actually render the stories. And this is pretty much what we expected it to look like when we started doing work on this. There'd be a small amount of time when you're waiting before you send the network request, a large network-bound time, and then a relatively large time where we're doing rendering. But once we started collecting data, we found that it actually looked more like this. And so that's not at all what we were expecting. There actually was a large gap between when the user started the application to when we actually sent out the network request. And on low-end devices, this was actually on the order of seconds, which was like, what? And so why is it that this actually was taking place? In most iOS applications, starting your app doesn't involve very much. You create a window, a navigation controller, your view controller, and you're off to the races. But when you're operating at scale and having many, many developers working on the same application, you have many features that people rely on, and you build up a lot of infrastructure to support that. So before we can even start to put the feed view controller on the screen, we need to set up, for instance, an exception handler, so that if the app crashes during the time where we're setting it up, we're going to know about it. We also need to have a network infrastructure to make sure that our network is very fast. We need A/B testing so that we can make sure that the user is in the right group. We need analytics so that we can monitor how the app is doing in production and continue to improve the user experience. We need to set up our persistence caches. We need to do authentication and login. We need to start up our app modules and app services, all of these things that are necessary to make the app really great. And although an engineer who hasn't worked at scale might look at this list and think we're just doing a bunch of junk that we don't have to, each of these services are actually vital to making the app successful. And smart engineers had good reasons for putting these things on the startup path. And so how do we solve the issue? Well, the first thing that we reached for in these sorts of situations is we should refactor these services and make sure that they only do the minimal amount that they have to do, make them faster. And that's a reasonable approach to start with. We did that with the first thing in our system, and it shrunk everything down and moved it over. The problem, though, is that in the same time while we were doing this refactoring, more services were popping in. And so now Composer needs to fetch the privacy so that it's more performant. And Graph Search is doing setup. And this is actually the inevitable nature of innovation. When you're moving fast and you're continually to develop new features that the user is going to love, you need to be able to add these services over and over and over again. And so you can't actually just say, I'm just going to refactor the things and make it faster. And so what we did is we took a step back. And we said, what do we really need in order to send our network request? Really, there are three things. We need the user's authentication token. We need to know who the user is that's sending the request. Then we need to know where that user is in feed. What was the last set of stories that they saw so that we can send things from before that? And then we also need the feed request configuration values, what A/B test groups they're in, et cetera. This doesn't actually need all of the infrastructure that we looked at up front, although the infrastructure is necessary to run the app and make it successful. And so we actually know all of this information every time we get a feed network response back. And so what we decided to do was, in a secure way, we persisted the network request we thought we were going to make the next time the app started to disk. And so what happens is, then, is as soon as the application starts, before we boot any of the infrastructure, we read what we think the feed is going to request from disk. And then we immediately send that request off to the server and start it processing. And then we go on with the rest of our application setup. At some point, the feed module is going to get booted. The view controller comes on the screen, and it says, here's the feed request I want to make. At that point, we do an equality check between what the feed is wanting to send and what we sent earlier. If they're not the same, then we just cancel the outstanding request or throw away the data we got back, and we haven't lost anything. But in the case where they are the same, we can actually immediately say, here's your data. We guessed what you were going to do. And so that moves the feed UI display down like that and improved it a whole bunch. The next thing we went to do then is how do you organize once we've done that request? What takes place? And again, we took a step back and we said we want to break this into parts so that we can understand what's going on. And so we know once we hand this request off to the networking system, there's some period of time between when we hand it off and when that request actually gets on the wire. Then, from the point in time at which the request was on the wire, there's some period of time before the server receives it. And then again, there's some period of time while the server is processing that request, figuring out what stories to send back. And then there's the actual transfer from the server back to the client. And then once we've actually received the response, we have to parse it, turn it into the immutable value objects that we talked about last year, and then hand it off to our UI. So once we started looking at this data, again, we found something that we weren't necessarily expecting. We actually saw that there were several hundred milliseconds between when the request was constructed and handed off to the networking system and when the request actually hit the wire. Why is that? Well, on a cold start of the application, this is going to be the first time that you actually are making a network request to your server. And that means that we don't yet have an open and secure TCP connection, which means before we can put our bits on the wire requesting the server for it, we have to establish a secure connection with the server. And establishing a secure TCP connection actually takes 3 round trips to the server, which on a low latency network stack, you're talking on the order of several hundred milliseconds, where you're just sitting waiting. And so in the longer term, we'd like to be able to solve these solutions by doing things like caching the SSL certificates locally. But we said, what in the meantime could we do to actually cut out that period of time? And the solution that we came up with is something we call UDP priming. And so what we do is immediately after the request is given to the networker, and before we even attempt to establish a TCP connection, we start blasting the server with a secure UDP packet saying, here is the request that we're going to make. Now, UDP doesn't require establishing a handshake, which means there's some period of time that the request is actually not going to get to the server. We don't have any guarantees. But that's OK. If it doesn't get to the server, we're in the exact same situation that we were in anyway. And when it does get to the server before our actual request, the server can start that request before we even send it up to it. And so hopefully, by the time the actual request gets to it, it's just sitting in memcached, and it immediately turns it around with no processing time, which shrinks all of the rest of the things after it. All right, so we've optimized everything up to the server receiving the request. So what can we do from there? The next chunk that we looked at is how long does the server take processing the request for stories, and how can we cut that down? And so that's this chunk. And in looking at the data, it quickly became apparent to us that this was primarily a function of how many stories we were requesting. For historical reasons, at the time when we started this, we were requesting a total of 10 stories and asking for that in 2 batches. So give us 3 stories, flush it down, then give us 7 stories and flush it down. But there were times where we didn't have that many stories, and when we didn't have that many stories, we noticed that every chunk was actually smaller, because the sending of the response is going to be fewer bytes over the wire when you have fewer stories. The parsing is going to be fewer things to parse. And so we said, why don't we actually stream these one at a time? Instead of doing everything all at once, we'll batch it into really small parts, give us 1 story, flush it down, give us another story, flush it down. And we did a whole bunch of different configurations, figuring out what the actual structure of that should be. But it ended up being essentially 1 + 1 plus some other stories afterwards. And that cut down on the actual transfer time, that cut down on the parsing time, and that saved us, again, several hundred milliseconds. And then that brought us to the last section, which is actually from parsing to displaying our feed UI. And this is where we thought, intuitively, most of the work was going to be. But it turned out that this was the small part on the end. And when we actually started monitoring this data, the slow part was not even the actual rendering of the stories most of the time. That was actually pretty well optimized with our component system and rendering. But what we found is that all of the services that had gotten started up inside of the app were then competing for resources with the ability to parse and display the stories. And so what we did is we built a tool that enabled you to, instead of saying, I want to start this service when the application starts, we said, I want to start the service once the application has reached a steady state, which we defined as the feed has loaded all of its stories, and now we're off to the races. And we moved the most heavy offenders that were causing contention onto that system, and that, again, saved us several hundred milliseconds and got us pretty much to the place where we're at today. Now, there still is a lot more work that we could do, and we're working on it, but we're really proud of the fact that we were able to get as much done in the 6 months that we did. And so, in summary, the first thing that we wanted to do, that we always did, is we break down the problem. We want to measure it with the data of how long the times are actually taking in production, because almost always you're wrong with your intuition as to where the time is being spent. Once you break that up, then you drive down each of the parts independently. The solution that we basically did on most of these is essentially a cache. How do we make the time that we're doing processing speed smaller? And the answer, most of the time for us at least, was we're going to cache the value so that the value is already available. And then faster app, which means happy users. And so that's all we have.